All right, let's go ahead and kick things off. Make sure I get my mic right in front of me. I usually have it off to the side when I am not lecturing. We'll go ahead and start with today's office hours. And don't forget, there should never be any confusion of what office hours it is, right? If you go onto your hub, this is the Unit 2, so we're going to look at the Unit 2 hub. Video links. They are the times that are the office hours. All right. But if you're Unit 1, as I always say, you're more than welcome to stay. You are more than welcome to stay. All right. Let's go ahead and see who is here. I see Maths Lectures is here. Mr. or Mrs. or Lectures. I see Ramsey K is here. I see Jabril is here. Welcome, Jabril. Suleiman. Welcome, Suleiman. Paulino. Welcome back, Paulino. I see who else we see here. I see Ephraim. Welcome, Ephraim Emmanuel. Hello, Emmanuel. Nice to see you back here again. I see Derajay. Hello, Derajay. I see Fatima, name that I've come to be familiar with. For good reasons, of course. I am doing fine, Fatima. I am doing fine. Hope you are doing fine as well. I see Joseph. Welcome, Joseph Esau. Hello, Esau. I see Abdul joining us from Pakistan. I see Joseph Marie Alba from the Philippines. Welcome, Joseph from the Philippines. Ephraim, I see Nelusha, and I have some doubts to use transformers before train test split or apply individuals after the split. Okay, we can go ahead and talk about this idea of a train test split. Go ahead and clear this out. Put this here. Train test split and transformations. We'll start with that for today. I see Abdo saying, can you please explain the concept of CVD? All right, I can talk about that today, the concept of CVD. Okay, all right, let's go ahead and kick things off. Let's go into the pod. And remember that I always post the office hours notebooks. I always post them. Of course, I can't post them immediately, but I always post them after the lecture, after the office hours. So I'm going to duplicate one that I already have because I want to use as the template for today. Since there's going to be some code that will be the same, I don't want to have to write it all out, right? The more code you write, the more likely there is to be a mistake, at least for me. Change the date. Change this to 9. Go ahead and open that up. Okay. Do kernel, restart and clear output, and let me just delete things that I don't need. All right, let me go ahead and get back to just a piece that's has my workflow. So let me just delete some things. I need that. I need the data set. And let me just delete all this other stuff. Okay, I think that's a good place to start off with. I might delete some additional things. Okay, so it's going to run these cells here. It's going to import our data, and I'm going to go ahead and create a train test split. And the train test split is necessary because if I want to teach you some grammar, I want to teach you a language, and languages have grammar, right? You think of grammar as a set of rules, patterns to take a verb, or this here specifically verb, or some sort of part of speech, and how to transform it to be part of a sentence so that one can understand. So in I would say all languages, we have verbs, and then we conjugate those verbs to reflect what tense they refer to: present tense, future tense, past tense, other tenses that I don't know the names of because I'm not a grammar person. But we all have that in certain languages. Conjugation's easier than others, right? So imagine if I were to teach you the grammar, I want to make sure I am able to evaluate. I want that you actually learn the grammar. You just didn't memorize the patterns. That you can be given a new word you've never seen before, and you know how to conjugate it, how to put it into a sentence. So because of that, we often will do a train test split. So let me go and import the train test split function. From sklearn model selection, import train test split. And do the train test split, x, y, test size, 0.2. And I'm going to set the random state to be 0. It does have to be any integer. It can be any integer. We're going to specify it so we can specify in instances of randomness so we can actually have reproducible results. And I will do a train test split, train on training, evaluate on testing. Okay. So let's train our model. Here's our model here. And let's fit on the training set. So one thing to be aware of, as someone pointed out here, is you use, let's see, I have doubts when to use transformers, before train test split or after. You do the transformation after the train test split. One of the very first things you want to do in machine learning is perform a train test split. I would even say it is literally the first thing you do. The reason being is because the test set you want to hide away. You want to take that test set and hide it away, because you do not want to be influenced by that test set. The more influence, the more direction we take based upon the test set, the more we're going to taint the test set. We're going to ruin the test set. If I start using the test set to gain information or be influenced about how I craft my model, I am biasing my selection. I am letting the test set influence model selection, and it will no longer be a true test set. So I would say literally the first thing you want to do is perform a train test split. Take a portion of your data and hide it away, and do not let the contents of that data influence how you craft your model. Even if let's say even if you say, oh, I'm going to do some data exploration before I do a train test split. I want to explore my data before I do a train test split. Well, you run the risk of, you do visualizations, in some sense those test points are in the visualization. So in some sense they are going to influence, they might influence you. So you want to do a train test split right off the bat. And what is a train test and validation split then? So what that means is that we can take our data, which was called X, which had about 20,000 rows, but now we've split them. We've split our data set into a train set. That's 80%. It's 80% of this. And a test set. That's 20% of the original data. And then the question becomes, so what is the difference between testing and validation? It goes into some subtlety here. A validation, we can go ahead and sketch this out. So we have our data, and we do a train test split. 80 and 20. Test and train. Now, in order for us to go about tuning our model, what do we mean by tuning our model? We mean by the systematic way we go about choosing the configurations of the model, the hyperparameters of the model. For example, I want to know, going back to that question that was raised that we're still going to answer, is which is better to use, min-max scalar or standard scalar? We want to know which one's better to use for our example here. In order for us to choose if we should use standard scalar or min-max scalar, we need a third data set. A third data set for validation, for choosing what model we ultimately pick, what model we ultimately develop and use in production. So we're going to split our training data set into further so that it is 60, 20, 20. It's validation. And of course, it's not drawn to scale, right? It's not drawn to scale, but bear with me. In fact, let me just fix this up. It's a little better there. 60, 20, 20. So what this means that we're going to train on training. We'll use 20 for us to guide us in picking our model. Maybe what transformers to use, what hyperparameters to use, are going to guide us to choosing the best one. And then 20 for testing. And testing is going to be the last thing we do for us to measure how well our chosen model does on data it has never seen before. And we're going to make sure, we're going to take a promise, take an oath, that we're not going to let that test set influence our model selection. Because if it does, then we might just get a model that just does well in the test set. And it's not going to, no guarantee of how well it do with data it has never seen before or it has been influenced by. You take random ones, correct, Bakal. You take random cuts. You need some randomness involved here. Now that's the difference between train, validation, and test. Let me know if there's any questions right now. I see Nancy is here. Welcome back, Nancy. I see Shaima is here. Welcome back, Shaima. Nice to see you at the top of the office hours. Questions people have before we go into something that's problematic about this setup? I see someone saying here, what if we want to predict a value using a model for a single test case? Should I apply standard scalar? Yes, you always apply, if your model is scale and predict, you need to make sure that any new data goes through the same set of transformation. Because your predictor learned from transform data, so any new data needs to undergo that same transformation step. When validation is used, doesn't number of training data lessons? Yes. So Ratnandeep is bringing up a good point here. Is that validation is important for us to choose the best hyperparameter. But notice how we have less training data. We have 60 instead of 80. We have 60 over 80. And we understand that the more data we have, generally speaking, we're going to do a better job. Right? Rule of thumb in machine learning is that the more data you have, the better your model will perform. No guarantees, but it's a rule of thumb. Right? It's a guiding principle. It's a guide, not necessarily a rule. Not an exact rule. And do we aim for overfitting on the validation set? No, you don't aim for overfitting. You aim for generalization is what we're aiming for in validation. Do we perform the same model for validation? Yes. Yeah. Well, actually, the validation, you come up with candidates and you evaluate each one on the validation set. The validation set, you're going to run it against multiple models because the validation is all about figuring out which one is the best one. Is it like a compromise? It's a compromise. In fact, in this course, we're going to make a lot of compromises, a lot of trade-offs. Life is full of trade-offs, right? We want it, in a real world, we'd have infinite training data, right? In the real world, we'd have infinite training data. In the real world, we wouldn't have to do machine learning, right? In the real world, we would know the answer off the bat. So yes, exactly, Bakal. This is a trade-off. It's a trade-off. It's just something I have to make, a decision I have to make, a compromise. It's annoying, but just because we have to compromise doesn't mean we have to make such a big sacrifice, right? We have to compromise, but do we have to make such a big sacrifice? And the answer is no. We don't have to make such a big compromise. We don't have to. And we're going to learn how we can not make such a big compromise. All right, didn't quite understand the difference between train, test, and validation. Okay, yeah, so I can take it from the top. It's a very important concept, so I don't mind taking it down, taking it from the top. It's very important. Let's say this is my workflow. I'm going to scale my data, then I'm going to have a predictor. Machine learning predictor. I know how I can put this in a pipeline. Now the question is, what scaler should we use? Should we use min-max or should we use the standard scaler? And we talked about that, the min-max scaler will probably not do so well if there's a lot of outliers. So we can kind of get a feel for which one we think would do better, but unless we run the experiment, we don't know. Machine learning involves experimentation, trial and error. Of course, we should be systematic in how we carry out those experiments. We don't just run experiments and forget what we did and run more experiments and forget what we did. We carry them out systematically, just like we're in a lab. Right, our lab here is a computer. The computer lab, I guess. So we want to determine what is the best scaler. We probably think a standard scaler, but maybe min-max will be the best one to use. So what we're going to do is we're going to do a train test split. X train and X test. Because we want to understand how well the model will do on data it has never seen before. Data it has not touched. Train on training, see how well it does on test. But if we choose the best scaler based upon our test set, then we no longer can say that we understand how well this model will do on data it has never seen before. It's subtle. I get it. In fact, it took me a while to really wrap my head around this. But if I choose the winner on the test set, all I really know, or what I'm guaranteed, is that it maybe just so happened to did well in the test set. Right? It's like, I'm going to use cricket as an example. I don't know cricket, but I know baseball. I know American baseball. So I think it's somewhat the same. So let's say I'm going to send out a batsman. I guess that's what they're called in cricket. Sorry if I butcher this example. I'm saying cricket because we have a lot of people from India, so I will, I would use cricket as an example, and other regions in the world where cricket is popular. I believe it's also popular in Pakistan. I could be wrong, but do let me know. And if I want to send out my best batsman out there. If I don't know who the pitcher is, the person who throws the ball, I want to send out my best batsman. I don't want to send my best batsman who just so happens to do well on a particular pitcher. I don't want to send my best batsman who's just so happens to be good on a given pitcher. I want to send the best batsman in general, regardless of who the pitcher is. I want to send my best model regardless of the test set. So that's why I should not use the test set to choose which model I use. And yes, math lecture, you need to apply the standard scaler on that single data point. Yes, it does. That you need to apply the transformation on a single data point. Because the model was learned on scaled data, so any data you bring in to make predictions needs to be scaled. Ah, yeah. Yes, cricket is too popular in Pakistan. Too popular in Pakistan. So hopefully I sort of made sense in this cricket example, where I want to choose a model that will do well regardless of the data. I don't want to, it's very hot here in my room, so that's why I'm taking off my coat, so bear with me here. Maybe I get overheated when I get excited. So I want to choose the best model given a generic test set. So you see the dilemma here, that I need a different data set to choose the best model. So I need data to train the model. I need data, so train to build a particular model. I need a validation set to choose which is the best model, and a test set for me to understand how well the chosen model will do on data it has never seen before. We'll see the exact score method when we start implementing this in scikit-learn, so we'll reserve that and we'll explain what those different score methods mean, so I'll keep that point in mind. So let me recap that. We use training to build the model, we use validation to choose the model, and we use test to see how well the model will do on data it has never seen before. I see Tekle is here. Welcome back, Tekle. Nice to see you here. So hopefully that clarifies things. If you're still struggling, it's a bit weird. It's not a bit weird, but it takes a while to wrap your head around. At least I struggled initially a little bit. I actually don't need my headphones, so I don't even know why I have them on. There, how about that? I don't need headphones. It's very warm here. Okay, so we see this dilemma. We have this dilemma that I need to create 3 splits in my data. Train, validation, test. But it's annoying how I'm losing training data. I have to do it. It's a compromise. But I have to do it. It's so annoying. There's got to be a better way to lessen the compromise, lessen the trade-off. Right? Maybe we can negotiate, so to speak, and come up with the better terms of agreement. So that's what we're going to try to do. That's what we're going to try to do. We are going to say the following. We're still going to do a train test split. 80 and 20. Yes, this is being recorded. It's been recorded and posted on YouTube. So yeah. 80-20. However, we're going to take this training set, we're going to pull it out here. And we're going to break it into multiple folds or sections. 1, 2, 3, 4, and 5. We are going to break our training data into 5 folds. 5 folds. And a fold is simply a split of the data. You know, we break it down to 5 folds. And what we're going to do is we're going to take, for example, we're going to take our model that was built with min-max, their min-max scalar, min-max. We take that model, we will build that model. We will build that model using folds 1, 2, 3, and 4. We build that model using folds 1, 2, 3, and 4. Then we will evaluate it on fold 5. And we come up with how well it does. We measure how well it does with fold 5. And we're doing this trade-off because we want generalization. We want model that doesn't just do well on data we used, but on data we have never seen before. That's why we're doing this. How does applying standard scalar on a single data point make sense? Well, scaling is just you subtract the mean and you divide by the standard deviation that you use. But keep in mind that the mean and standard deviation you use is what's learned from the training data. It's not the mean and standard deviation of that point, which I get doesn't make sense for that single point. You scale it the same way you used on the training data because that's what you learned from the training data. You apply that same scaling. And you have to apply that same scaling. So now that we trained on the combined folds 1, 2, 3, and 4 and 5, evaluated on 1, 2, 3, and 4, evaluated on 5, we do it again, but we train the model 1, 2, 3, and 5 and see how well it does on 4. And then we see how well it does when we validate it against fold 5. We repeat again, but we train on folds 1, 2, 4, and 5, measure how well it does on 3. Standard scaling is a type of normalization. Some of this language isn't quite consistent, but from my understanding, normalization means a way to normalize or rescale the data. Standard scalar is one way, min-max is another way. So notice how every fold has a turn to be the validation. Every fold has a chance to be a validation. And then we come up with the average across those five folds. For every fold, we can come up with a score, how well it does, and we take the average across those 5 folds. And we know from Unit 1 that averages can better insulate us against randomness. If I go out and measure if I go out and measure the concentration of some chemical in a river one time, that measurement can be widely off. If I take 10 samples from the river and I take the average, that average value will probably be closer to what is really true. Averages help insulate us against randomness. So this is called K-folds cross-validation. K-folds validation. And then once we do repeat the process again, but for our other model, which is our standard scalar, which I'll just abbreviate as SC. Does the score method be? No, it does not. It does not. The score method does not. I'll show you how you can implement it in Python. And I will get to maths lecture question 2 as well. So we repeat the process again for standard scalar. We train on 1, 2, 3, and 4, see how well it is on 5, 4, 3, 2, and 1, take the average, and now we have 2 averages. This is how well min-max did, this is how well standard scalar do, and then we choose the best one, and then we do a final retraining on the entire training data. So once the best model was determined by its average score across those K folds, generically K, then I retrain the best model using the entire training set. This is K-folds cross-validation. Notice I'm able to get away with using the entire training data. I'm able to better insulate myself to randomness by having 5 different K different validation folds. Someone is asking, this is for a financial engineering course? No, it isn't, but you're more than welcome to stick around. You're more than welcome to stick around. I won't kick you out of my office, so to speak. Okay. Questions people have before we implement this into Python and scikit-learn. I know we haven't focused on how to implement this, but we got to first understand what's going on before we try to implement it in Python and scikit-learn. Okay, let me know, but let's implement it in scikit-learn. So what I'm going to do is I'm going to say from sklearn model selection import grid search CV. This is a class that will allow us to do this validation for us very nicely, automatically for us. And we're going to give it a param grid, a dictionary, which expresses the different candidates for us to choose. And we want the step scalar. We want to either test out standard scalar or min-max scalar. And I got to import min-max apparently. So scikit-learn pre-processing. Import min-max. So this dictionary says, hey scikit-learn, I want you to choose which one, these are your two candidates for a step called scalar. And the reason it's called scalar is because, remember in my pipeline, I called that step scalar. So since I called that step scalar, this name carries over. I'm going to create a grid search object. The first parameter I give it is my model, is what the model to try out. And that's called model. I called it model. I give it the param grid. I give it how many folds to do. On the blackboard, on the whiteboard, I used 5 folds. An example, but I can choose how many to do. And I'm going to say 5. And I set verbose equal to 1, which will print out what's going on. Verbose set to 1 will print stuff out so I know it's actually running and what it's doing. This is going to take a while. It's not going to be instantaneous. So it's nice to see that it's running and we get some information about what's going on. This returns a estimator object, which I will call grid search. Questions so far? Questions about this here? I've not done anything besides set things up. I've set up my experimentation. I've yet to run it, but I've set up my experimentation. What if we put verbose other than 1? If we set to 0, we're not going to see any printout. If we set it to 2, we see more printout. Other questions people have? What are the criteria to choose number of folds? 5 is a good number. If you have more data, more patience, use 10. So don't use anything less than 5 is what I would recommend. Try to use 10 if you are more patient or have more data. The more folds you have, the better results you get, but it does require more and more time. Other questions people have? Okay. Do let me know. But this grid search object can be fit, and we'll give it the training data. So by fitting grid search, we invoke the k-folds strategy. Verbose will allow us for this message to print out. And that's what verbose is all about. It's saying, can you print us information about the training so we know it's actually running? Is grid search a linear model? Grid search is not a linear. Well, in this case, yes. Grid search is a linear model because we gave it a model that is a linear model. Grid search is a framework to tune your model, to best decide the ultimate model. Yes, and here we'll be choosing the two scalars. Exactly. So notice it ran. It said two candidates, right? Because we're trying to choose between scalar and min-max. Sorry, standard versus min-max. 5 folds. So that means we're going to train each one 5 times for a total of 10. So that makes sense. It did this, all what I did here, to carry it out for us. And now, if I want to see which one was the best one, I say grid search and I say best params. Oh, it looks like min-max was the best one here. What was the average validation score? There it is. It was 0.605. Why is this video labeled the 28th? I probably goofed. Messed up. That's why. I was careless and I messed up. That's why it's labeled the 28th. How does it do on training? Well, I'll just score on training. That's how it does on training. And now that I've chosen my model, let's see how it does on testing. So score on test. Remember, score accepts a data set in the labels, and it tells you how well it did on that particular data set. And there are 3 scores we derived. How it is on training. Let me just move this up. How well it does on training. How well it did on validation. How well it does on testing. And there are 3 measures of model's performance. So you thought we would use x-test and y-test to choose the best scalar. We don't want to do that. Because then our best candidate, we run the risk that we chose it because it just so happened to do well on what just so happened to be the test set. I'm not sure if you're familiar with cricket, Fatima, or baseball, but I want a batter who will do well regardless who the opponent is, rather than what just so happened to be the opponent I tested it against. And how do we know what is the model? We can look at best params. In fact, the model, we can actually pull out the model itself. Best estimator. Model best. I pulled it out now. And there it is. There was my best model. Does the training score is average of all folds? No, the training is how it is on training. Best score is the average. So this is the average across all K validation folds. Did the grid search train the model on the whole training set or of some of the folds of it? It training on a portion of the folds, but once it determines the best model, it retrains the model one more time using the entire training set. So I'll put a comment here. The best model, the best chosen model, was then retrained on the entire training set. So after K folds CV, it ran one more fit with the best candidate, but now using the entire training set. If you're curious about the individual results, they're stored in an attribute called CV results. There are the individual results there if you want to look at them one by one. So line 13 is enough to know what is the best model. Yes, best params tells me what was the best parameter it found. How many models does grid search have? It can do with it any model. The thing is, you give it the model. You give it the model to tune, to train, to use. So you provide grid search. You tell grid search, hey, here is the model framework that I want you to play around with. This is a dictionary that tells you what are the candidates. Go at it. So grid search can be used to test not only scalars but different regress. Yes, theoretically, yes. Theoretically, yes. The reason I say theoretically is because things will get messier because you also want to tune hyperparameters of your regressor or your predictor, and then it just becomes very messy. It just becomes a lot messier to keep track of things. Because, yeah, it just becomes a little messier. How about that? Oftentimes you just, in that case, you typically invoke a different grid search. What's a good score? A good score is a score. This is a business question. A good score, of course, would be 1. R-squared value of 1. Perfect. On a test set or a validation set. But I would say a good score is anything that will improve your current best practice. If I'm doing spam classification and I'm unable to identify any kind of spam, then a good score was one that does better than just guessing. So the best score is subjective. Do I have an expert system that I implement? I got to make sure that my model is, at the very least, does better than the expert system that's already been implemented. So it's one of those, it depends, right? Is your model, if you introduce it into your application, will it make your life better? Will you make more money? Will you help more people? That's how you assess it. This is Yusef here. Welcome, Yusef, from Nigeria. So back to, I think, a question I see here with maths lectures. How do I apply training transformers on a new test set? When I do grid search, predict, since I have a pipeline, it will undergo the transformation automatically. Since I'm using pipelines, scikit-learn will handle the necessary transformations. In fact, going back to your point, I can call predict on a single data point. I can say x test and I can say 0. It's a value error because it needs a two-dimensional array. So let me just say I want, let's see, 0, 0, colon. Get a value error. Got a 1D array. I can say 0 and just reshape this. Be 1 row, however many columns. There you go. What it's doing underneath the hood, it's basically taking that single point. I'll just pull it out. And then it's saying, okay, grid search, best estimator, pull out step 0, and it says single point T, transform, single point. And then after I transform that single point, I can pull out the individual predictor. And predict on single point of T. There it is. I get the same answer. That's the beauty of pipelines. It will handle those transformations for me. And since I learned how to transform the data, since I learned from the training data set the means and the standard deviations, I apply those means and standard deviations. I apply those means and standard deviations I learned from the training data to transform a single test point. I don't take the standard deviation and the mean of the single test point. I don't do that. I use what I learned previously to apply the transformation. So hopefully that answers your question about a single data point. So let me know if there are any questions, but now we've answered the question. Sorry, Mickey Rat, for you. I know you've been waiting for several days about which one is better, but hopefully it paid off and we learned how to systematically determine that. Let's see, Fatima says the chosen scalar depends on data used. It depends on the data, right? It depends on, sometimes the standard would do better, sometimes the min-max will do better. All right, I'm glad you thought it was worth it. I would say most of the time the standard scalar would be better. Yeah, print out single point, right, or just single point of T. I would say standard scalar will probably be the better one. Strictly speaking, the scaling, so yeah, it's just, yeah, I would just use it as a rule of thumb. I actually could go back here and bump it up to 10. I can probably bump this up to 10. In fact, I'll do that. I'll bump it up to 10, right? I just bumped it up to 10. Ooh, scalar was better now. So, if I bumped it up to 10 folds, now the scalar, standard scalar, is better. What's going on? So see what I did? I bumped it up to 10 folds, more folds, and now the standard scalar is better. Anyone want to guess what's going on? It's something we learned in Unit 1. is easy to calculate. Not necessarily easy to calculate for 10 folds, but thank you for answering. So transformers only get fit in transformations during training pipeline. For tests that the pipeline only applies. Yes, correct. And when a test, it only applies the transformation. You don't refit the transformer on a test set. You use what you learned on training to perform the transformation. All right. Any guesses why I get a different result now? Any guesses? Why was 10 folds? Why when I bumped up the folds, doubled the folds, scalar was better? I see Safe Mahdi. I have an issue facing VC3. This is Unit 2 office hours, by the way. So come back later today when Russ will do Unit 1 office hours. But if it's the VC, but for my guess, Safe Mahdi, is you need to consider that your class can handle multiplication of point objects and numeric objects. It means something different to multiply 2 points and multiply a point with a number. So make sure you handle both cases. With that said, this is Unit 2 office hours. So that's all I would say about that. Come back later when Russ is doing Unit 1. Min-max might have changed when we made many folds, I guess. So not quite. So what's happening here? Yeah, it's a bit tricky. It's a bit subtle. This was a difficult question. It's a difficult question. Essentially, we are running an experiment. We are running an experiment. And thus, experiments have errors. No worries, Safe. No worries. So experiments have errors, right? All experiments have errors. And we know. So what we are observing here is a sample error. So in other words, if I want to determine, I have two schools. Two schools right next to each other. School 1 and school 2. And here's a street. And this school wants to determine which students can jump the highest, right? Is it school A or school B? Which students in what school can jump the highest? If I go into school A and I randomly pick 5 students, and I say jump, I measure how high they jump, and I took their average, I'll write it down. I go into school B and say, hey, you 5 students, jump for me. They jump, I measure, I take the average. It looks like an apple. It looks like an apple, yeah. And I come up with that people in student A, they jump 2.1 feet. I don't know what's the average height people jump. 2.1. In school B, it's actually 1.2. Assuming, 1.9. 1.9 feet. Can I easily declare that students in school A are the better jumpers? Can I make that conclusion? No, right? Why can't I make that conclusion? Right? We say no, right? No. Why can't I make, why not? Why not? We all agree that no, I cannot make that conclusion. Why can't I? Yeah, so we all agree. Thank you. We're all in agreement here. I didn't use a different sample size. I still used 5 and 5. I used 5 and 5. Sorry if I misspoke and I said a different number, but I used 5 and 5 sample size. But you're on the right track about sample size. This is just too. There's only one person that can jump to that height. You picked We picked a very small sample size. In fact, if I redone the experiment and I chose 100 people. If I choose 100 people and now the average for A is 2.0, yeah, small sample. And B now is 2.2. So this was a sample size of 5. This is a sample size of 100. And I get different results. Hey, sampling error. Yeah, exactly, Anthony. Sampling error. That buzzword we learned in Unit 1. Now, can I better trust the results? Now that I take 100? Yes, now the effect of individuals are minimized. So now, hopefully, we all agree that using 100, we can better trust the results. I think we all logically believe we can better trust the results. So Mickey Rat is sort of on the right here. Is like, wait a minute. We're running experiments. Can't we come up with a confidence interval, right? Can we get z-scores and p-values and confidence intervals? Exactly. Better than what we have here is what we do is we can come up with confidence intervals. We have sampling, and we learned how to do that in Unit 1. We can say that since we cannot tell everyone in the school to jump, it's got 1,000 students, it's going to take too long to really do that. It'd be really long. I can probably just take 100 and do some statistical analysis to come up with the average student in school A jumps 1.2 feet plus or minus 1, 0.05. How about that? And B, they jump 2.2 plus or minus 0.05. So now I can better conclusively say that yes, there's a statistical difference, statistically meaningful difference between B and A, school A and B. So what's happening here is that really these two scalars, they're going to get different results, but statistically speaking, their results are the same. So it just so happened to be that one did better when I had 5, one had better when I did 10. So we could come up with statistical meanings, and we'll leave that for future office hours. But I can say 100 now. And let's see which one is better with 100. Standard scalar, 100. I can probably trust that standard scalar is 100. However, 100 is impractical when we have more complicated workflows. We'll have to pick this up tomorrow. We'll wrap this up tomorrow, but I think we had good discussions. So with that said, everyone, take care. Have a good rest of your day, and we'll see you back here tomorrow.